My name is Oscar Antommattei. I'm the Chief Concrete Engineer for Kiewit Engineering. It is a pleasure to me to talk today about the thermal aspects of concrete design and construction, a view of the North American experience. In our presentation today, we're going to be talking about mass concrete. We use mass concrete especially because it allows you to discuss different aspects of the thermal behavior of concrete. And with that, we're going to be also presenting an example of a standard that we developed in Canada for the Canadian Standards Association, an example of a project that we complete in the United States that allow you to use a lot of different diverse concepts for mass concrete. In our introduction today, I want to make sure that we understand a little bit of the perspective of concrete, the perspective of design and construction in projects. And first, let me talk about my point of view. Coming from Kiewit Engineering and the type of design and construction work we do, I am heavily involved in different infrastructure projects all across North America. As you can see, the variety of projects go from having dams, bridges, buildings, and special structures like you can see on the bottom that are related to the immersed tube tunnels that we do sometimes in some of the key projects in the United States. Additionally, when you think about concrete, what is the perspective you have about concrete? This is an image from a concrete project that we had in Colorado, and it's very interesting because we have all different types of concrete scopes. We have a bridge, we have a site, we have a building, we have paving work to do. So you think about what will be the conditions and applicable standards, specification requirements, codes that are going to be related to all these areas of work. Are you going to expect to be the same? Are you going to expect the concrete that is in the field, in the site, be the same as the concrete in the bridge? Or the mass concrete in the supporting the approaches of the bridge? Or maybe in the more architectural concrete sections that are inside the building? And most likely you're thinking, obviously, it's not going to be the same. So as you see that the concrete in different parts of the work is not going to be the same, then you start thinking about how concrete can be specified to be the same in different parts of projects that are going to have different requirements. How is that going to impact constructability? How is that going to impact design? How is that going to impact the expectations of the client, the expectation of the designer, the way you're going to plan your means and methods, the way you're going to select the mixed proportions for the different applications, how you're going to place the concrete, how you're going to finish it, what's going to be the temperature limits you're going to implement in all these different sections. And all of them are going to have different answers. But it's important to understand that. So when you look at this presentation, you have the mindset of there's always going to be different applications, different points of views, and different reasons to make those decisions in the design and construction of a project. Now, as I said, the focus today of our presentation is going to be on mass concrete. And the opportunity for mass concrete to discuss different topics related to the thermal aspects of concrete is very good. Because we're going to be able to talk about the ability of the concrete to generate heat, the temperature of concrete at placement time, and even then the temperature limits associated to controlling thermal behavior of concrete placements. So the first thing will be understanding what is mass concrete. What is the type of mass concrete we're talking about? Because the traditional mass concrete, which is a traditional concrete that we have been looking for many years as part of dams construction, those are very different to the thermally controlled concrete, as we call it in the United States, for the mass concrete applications that are going to go into bridges and buildings. And let's see the difference. The main difference in traditional mass concrete is going to be you're likely going to have a lightly reinforced structure, where the majority of the structure is going to be constructed also in sequential placement. So you're going to have concrete built up next to each other, and you're going to have pretty much a volume created by all these different placements. All of that is going to impact also that you're likely going to have lower strength requirements or later age strength requirements. So you can expect the concrete is going to be different than the thermally controlled concrete. Thermally controlled concrete is mainly used in high-rise buildings, foundations, bridges, and what you're going to expect from that type of design is going to be heavily reinforced. And not only is it going to be heavily reinforced, it's going to be typically isolated structures, not going to be like a dam, it's going to be isolated, but also you're going to have much higher strengths. The strengths are likely going to be at early age, the strengths are going to be much higher than what you expect traditional mass concrete. So then what? When we talk about mass concrete here, we're going to be a little bit talking about traditional mass concrete in some applications, but also thermally controlled concrete. But what we need to think about is that there's going to be always different applications where you're going to use the same concepts, but the limits, the way you're going to design for controlling the temperature, the way you're going to find thermal control measures is going to be different. And that's why I want to make sure that you understand those two types of mass concrete as we go into this discussion. So a very common question that comes when we're talking about mass concrete. What is mass concrete? And in this chart, we're presenting the concept of cementitious materials content and minimum dimensions. The larger the dimension of the concrete, the higher the risk for behaving as mass concrete. The higher the content of the cementitious in the mix, the higher the risk of mass concrete. And what you see here is all associated to temperature limits like 70 degrees Celsius as a maximum temperature and the 20 degrees Celsius as a maximum temperature difference. Those are the default values typically used to define mass concrete, and that's why they're used here. But if you have other limits, then obviously you have to consider different definitions for mass concrete in terms of the numbers that you're going to use to draw the line where mass concrete is and where it's not mass concrete. But in summary, the concept is the larger the structure, the more cementitious, the higher the risk for behaving as mass concrete. So when we talk about mass concrete, we need to talk also about adiabatic temperature rise, which is the ability of the concrete to generate heat without being affected by the environment, without losing heat to the environment. The ability of that mix to generate heat is mainly affected by the cementitious content and by the type of cementitious materials. A traditional mass concrete would typically see a lower adiabatic temperature rise, which is expected. Typically, we see that it's below 45 degrees Celsius, and a thermally controlled concrete we typically see to be higher than 45 degrees Celsius. That's a very common observation we see in practice for adiabatic temperature rise. And talking about adiabatic temperature rise, you need to think about what are the tools available for you to assess a mix. And this is what I'm showing here. I'm showing here different concepts that we have discussed in different committees in the North American market. And the first one is a simplified approach. The simplified approach is a simple thing of just qualifying what is the materials you're going to use. There's going to be a factor associated to that material, and then you do the calculation by a simple mathematical equation. Computer modeling is typically used also as a way to assist yourself in those calculations. So you may use finite element analysis to generate a model that can allow you to generate heat and then trap the heat and then qualify that heat so you have an adiabatic temperature rise value. Semi-adiabatic testing is one that I'm going to show in the next slide, but it's very commonly used in the North American market because it's a simple, heavily insulated block. You put the concrete, you qualify the measurements of temperature in the concrete inside and outside, and then you'll be able to make the calculations and use computer modeling to qualify the adiabatic temperature rise. Adiabatic testing by the test method is available, but it's rarely used. Its testing is rare because not many people has it available, and it also has limitation with the time and the cost. Then field placements are, in some cases, you have something like a crane footing that you can instrument and monitor and then protect the surfaces from losing a lot of heat so you can qualify the heat. And then you use that information by putting the values that you got in the field with computer modeling and then qualifying the full adiabatic temperature rise that way. And other methods that exist are more hand calculations provided by ACI, like a Smith method that is available in ACI 207.2R. But those have been found to not be as exact or as good predictors of the behavior of concrete. So in the next slide, I'm going to show an example of semi-adiabatic testing and how you use it to qualify the concrete properties. To determine the adiabatic temperature rise using the semi-adiabatic testing block, you see here on the left side of the slide a set of photos that shows you the heavily insulated block. It's typically a R30 value all around the surfaces, so you retain the heat pretty nicely. You put 1 cubic meter of concrete, you put the cap, and you're measuring temperatures inside and outside that concrete. So when you get to the middle here where I show you the computer modeling, the first data set on the top is pretty much the data that you gather from the block. And once you get that data from the block and you put it in computer models, you can calibrate that ability of the concrete to generate heat. And then on the bottom graph, what you're going to see is then in the green graph is showing you there that once you use that information, you put in the calibration process with the computer model, and then you generate an fully adiabatic behavior in the model, you're able to understand what is the adiabatic temperature rise of the concrete. Here on the right, where it says ATR calibration process, it shows you everything I just discussed in one figure. measurement of the semi-adiabatic testing data, computer modeling, and then by combination of those two, you're able to calculate the full adiabatic temperature rise. Now, when we talk about fresh concrete placing temperature, it is important to understand what are the effects of that. Higher temperatures can impact the fresh concrete properties, the thermal behavior, shrinkage, and even affect long-term durability and ultimate strength. So what are the limits that the industry provides in the North American market? And this is going to vary by placement attributes. A mass concrete expected to have a minimum dimension large enough, you're likely going to expect that there's going to be limits for lower placing temperatures. Not always the case if you have a thermal control plan that justifies that you can use higher temperatures, but in typical limits that you see 70 degrees to 95 degrees Fahrenheit, which is 20 degrees to 35 degrees Celsius, is typically the maximum temperature limit for placing concrete temperatures. And then the minimum, which are provided more for allowing adequate heat of hydration and strength development, is 5 to 10 degrees Celsius. So these are the very common temperature limits that we can see in the industry in North America. When we talk about mass concrete and temperatures, we need to talk about maximum concrete temperature limits. And why is a concern? Well, you want to make sure that the concrete develops strength and is durable. So now, what are the temperature limits that the industry provides? In ACI, for example, you would see a 70 degrees Celsius with or without mitigation. So what does that mean? That regardless of what is the concrete ability to resist a higher temperature, it doesn't matter. They have a 70 degrees Celsius limit as a default. However, when you look at the additional requirements or additional options provided to the specifier in ACI 301, you can see the allowance to go up to 185 Fahrenheit or 85 degrees Celsius. When you have mitigation with SEMs, with supplementary cementitious materials like fly ash and slag. So the key is that if you don't have any mitigation provided as qualified by ACI, then you need to maintain 70 degrees Celsius maximum limit. However, if you allow to be used some additional cementitious materials like fly ash and slag, then you can tolerate higher temperatures. And that temperatures can go up to 85 degrees Celsius. Now, the standards recognize pretty well that greater than 85 degrees Celsius is not permitted. In such case, you have to justify the TDIFF durability with testing, and that's something that has been provided given the research available and the results and the different options, but there's no consensus on exactly what is that test method that can be used. The alternatives for acceptance are allowed, are provided by ACI, and people can use it given the materials available that they can provide for mitigation of higher temperatures. In this case, you can see an excerpt of ACI 301 where we show the temperature limits, and you can see the maximum temperature limit on the left, and they always specify to be more of a unless otherwise specified, and the reason for that is that ACI 301 provides optional requirements, and the optional requirements allow the specifier to determine that there's a higher temperature limit that can be used, and in this case in ACI 301, it's clearly defined that you can go to 185 degrees Fahrenheit, which is 85 degrees Celsius, if you use a minimum amount of supplementary cementitious materials, as you can see here. Here you can see the supporting information from ACI 201, where you can find in ACI 201.2R16, table 6.2.2.2, that you have all the qualified prevention methods that are allowed by ACI to ensure that we prevent delayed triggering formation as concrete get exposed to higher temperatures. As we talk about mass concrete and temperature limits, it's important to understand the maximum concrete temperature difference limit. It is intended to control thermal cracking. And this limit is important to understand that it's a temperature difference that occurs between the core and concrete within that surface, typically assumed in the United States and Canada to be the location at where the rebar near the surface is. So it's important to understand that because there's other concepts of temperature differentials that are sometimes discussed that are mainly related to the more mass gradient occurring between the maximum temperature and the equilibrium temperature. That's a very common term that is used for traditional mass concrete. But the temperature difference limit associated to standards in the United States and Canada is related to the temperature difference between the core and the surface. So that's what we're going to be talking today. And the industrial limits that you see around is typically the 20 degrees Celsius limit. It's a fixed limit. So regardless of the concrete development of properties, the concrete ability to resist the different differentials is 20 degrees Celsius. Now, ACI 301 and the Canadian standards recognize that you can go into implementing different temperature difference limits. In Canadian standards especially, we recognize the ability of the concrete to tolerate different temperature differentials depending on the properties of the concrete. Sometimes it's allowed to go by incremental limits. In that case, you need to establish a fixed incremental limit that doesn't exceed the 25 degrees Celsius. And sometimes you can go into using more of a performance-based testing and analysis to show that the concrete can tolerate much higher temperature differentials, and they're qualified. Here in ACI 301, as an example, you can see the mass concrete specification that requires a maximum temperature difference between the center and surface of pavement shall not exceed the 35 degree Fahrenheit, which is 20 degrees Celsius. Now, when you go to the optional requirements, the standard also allows you to go into using different temperature difference limits. And you can use anything different than 35. Obviously, it explains the qualification and that it depends on the properties of the concrete, but it's important to qualify that that's a ability to change the temperature limit using ACI 301. And here I'm going to show you, these are the more common examples that we have adopted in Canadian standards. You can see that there's a fixed limit of 20 degrees Celsius. If you have a lower coefficient of thermal expansion, you can use the 25 degrees Celsius fixed limit. If you can justify the ability of the concrete to develop strength with time, you can use the step increase or the linear increase, which is one of them. Either one of them are going to be an incremental temperature difference limit. And then the more complex, which is used with testing and analysis, which is a performance-based temperature difference limit. In that case, you have to test the mix, exactly the mix you're going to use, and then provide the adequate information for qualification. As part of the discussions with mass concrete, it's important to understand thermal control planning. Thermal control planning is a tool to manage and execute the mass placements. It helps you understand the behavior of concrete and the challenges. And then once you understand the behavior and the challenges of the concrete and how you're going to place it and the temperature limits and the measures that you're going to use to protect concrete, then you can provide a plan that helps you control and monitor temperatures, reduce thermal shrinkage, and minimize thermal cracking. When looking to implement a thermal control plan, it's also important to understand the different parts of the plan. It's not a one-time thing. You need to understand that you're going to have to see the different factors associated to the work, associated to the material's behavior, and how things are going to work in the field, and then provide analysis representative of that work. The analysis and model is going to help you to determine the thermal control measures that you're going to define in the thermal control plan. And then once you go to the implementation, in the implementation, you're going to have to then understand what are the different requirements that are going to allow you meet the temperature limits. Once you have those conditions selected and you have the appropriate, let's say, insulation or placing temperatures or the different amount of cooling pipes that you have to put on the thermal monitoring locations you're going to have to use to control and monitor that data, then you're going to have to go and understand what's going to be the ability to generate heat in the field, but also verify it and provide validation. That, I believe, is one of the most important aspects of thermal control planning. You implement it, you understand it, you go and put it in place in the field, but then you're going to have to provide data to make sure that the plan that you thought was going to work is actually working. And then it's likely that you're going to have to provide some revisions and updates based on that data. But that's extremely important, because thermal control analysis in computers are not going to be able to represent all the conditions in the field. So this process is extremely important. Implement it, verify, revise it, and then update it as needed. In this section, we're going to present some of the advancements that we have provided to the industry standards in Canada. And the first thing we're going to talk about is the temperature requirements for mass concrete per the section on mass concrete for the Canadian Standards Association 823.119. So what happened in Canada first is that we don't have a good description of the mixes proportions. So for the thermal control engineer, you typically do not have that information readily available. So we need to first assess adiabatic temperature rise as a property we need to consider. Now, what did we do? So pretty much we put a requirement to ensure that we qualify the ability to generate heat by the mixes. So now we have a requirement that the mix design needs to include the adiabatic temperature rise associated to that combination of materials. Even when they do not report the actual proportions of materials, you need to provide the adiabatic temperature rise value that has been calculated. And there's guidance provided for our calculation and testing of that adiabatic temperature rise. Then we have the maximum placing concrete temperature. Before, we always defaulted to a table 14, which is provided here. As you can see, the maximum temperature can go between 20 and 32 degrees depending on the size of the element. However, because now we improve the way to provide thermal control plan requirements, we also allow that if the thermal control plan can tolerate higher temperatures, then the concrete temperatures can be higher than this table. So that's why it says in absence of thermal control plan, then you default to table 14. However, if you have a thermal control plan, you can go directly to the thermal control plan and use those temperature limits that are provided. Maximum concrete temperature is one of the most interesting ones, especially for the market in Canada. So when we talk about maximum concrete temperature, and the limits that we define here are based on high volume SCMs or not. So what happened is, as I described earlier, in Canada, we don't have the ability to know the exact proportions of the mix, but we have the ability to know if the mix is a high volume SCM or not. High volume SCM2, for example, will be a mix with 40% fly ash minimum. High volume SCM1 will be a mix with 50% SCMs, fly ash. So in that case, a higher amount of fly ash can tolerate higher temperatures. So we then define without any mitigation, you need to maintain the 70 degrees Celsius. But once you start mitigating the mix with use of SCMs, then you can tolerate higher temperatures. That's why 75 degrees Celsius for high volume SCM2 and 85 degrees Celsius for high volume SCM1. And I think the most interesting requirement that we have now in the standard is the maximum concrete temperature difference limits. So in this case, similar to what I showed you earlier in the slides, we now have 4 different cases that you can use to implement maximum temperature differentials. The first one is going to be a default of 20 degrees Celsius regardless of the materials you have or the mix you have. The second one is going to be the 25 degrees Celsius temperature differential if you can qualify that you have a low coefficient of thermal expansion concrete, in this case less than 10 millions per degree Celsius. Then you get to the third option, which is what I define as incremental temperature differential. You can define an incremental maximum temperature difference limit as long as you do not exceed 25 degrees Celsius. And if you want to exceed 25 degrees Celsius, then you need to perform testing, modeling, analysis to qualify the ability of the mix to tolerate higher temperature differentials. And that's what we call the performance-based approach, where then you can define a higher temperature difference limit over 25 degrees Celsius. One important part of mass concrete is temperature monitoring. So something that we did here is at least put a brief description of the basics of temperature monitoring that we need. The temperature monitoring in the interior core, where we can expect the highest concrete temperature, and then the concrete temperature near the surface that needs to be monitored at a minimum of 1 location between 25 and 75 millimeters from the concrete surface. Something important to put and address on the notes is that sometimes we see people specifying temperature sensors for thermal control mass concrete in the corners, and we here clarify that if that is a requirement, it's only applicable to cold weather protection and is not a requirement for thermal control of mass concrete. A very important part of mass concrete is thermal control, and the Canadian standards didn't have any guidance or requirements for that. So we now expanded in the thermal control planning requirements to show that all these different items are required to be documented in a thermal control plan. And then obviously what this is important for construction is because now you can understand better the different measures that are taken, the methodology, the temperature limits, the different thermal control measures you can implement, and it has a better definition for design and construction of how you're going to be able to meet the temperature limits that are required by the specs. In this section, I want to show you a very interesting project we did in the west coast of the United States. It was a major facility. The facility was very complex. It's actually a stadium, but it has a lot of different challenges in the design. You can see the left side some sketches from the actual design of the different mass concrete elements. As you can see, a good amount of concrete and the dimensions here. We're talking about 8 to 13 feet for mat foundations, 5 to 6 feet thick columns, And we have obviously the precast blade columns in this case are a little bit thinner, but you can see it's very high strength too. So here's an overview of the different structures that we were looking at. Massive foundations, as you saw, between 5 to 13 feet thick elements, and also between 5,000 to 10,000 psi concrete. So some of the challenges were how can we control temperature without the use of cooling pipes, because these are heavily reinforced structures, and we cannot just be putting a bunch of cooling pipes without understanding the constructability issues we're going to have. So we were able to understand that and then discuss with the design engineer and construction team the different options that we have available. Now, the most important part of this project that I want to show is how we were able to optimize the concrete mixture. We have the requirement for low heat, shrinkage needed to be low. We have also strength requirements and how modulus of elasticity requirements. And we were going to have self-consolidating concrete. So you can imagine all the different challenges. So the first thing we did is select a low water demand, high quality coarse aggregate. By doing that, we were going to be able to then reduce the water demand. Reducing the water demand was going to require also for us to be able to reduce the total cementitious. The lower total cementitious was going to reduce the heat, right? But then we needed to have high strength. With the low water demand, we will also be able to reduce the water cement ratio and be able to use high fly ash content, which we needed to also reduce the heat. So a combination of factors, we were able to then optimize the mix in a way of selecting the right materials and optimizing the materials for performance. When we talk about performance, a key element for this project was to develop a performance-based thermal control plan. We were able to qualify the properties of the concrete and run analysis to determine a temperature differential that was much higher than the traditional fixed temperature limit. Instead of going into having now a temperature limit of 20 degrees Celsius, we were able to use concrete temperature difference limits of over 25 degrees Celsius, which then allow for a lot of value into moving faster in the thermal control planning and not having to retain the thermal control plan for so long without the need for cooling pipes. And that was a key element for the success of this project. So as you can see, something important to understand of this presentation is there's no one size fits all. And it's extremely important we understand the standards need to be updated and how we need to manage design and construction challenges in implementing thermal control plans. Something that I believe is one of the most challenging parts of implementing thermal control plans in consideration of performance is that the standards are outdated. They need to adapt knowledge to practice. This knowledge has been available for over 30 years in the industry. Develop and optimizing mixes, extremely important to reduce the heat of hydration. And then using temperature limits that are applicable to the behavior of the materials. Qualify those materials. Make sure that you understand the ability to generate heat in the mix. Make sure you understand how you can use SCMs for you to optimize the mix performance. And then be able to test and qualify the performance-based limit. Implementing thermal control plans is extremely important, and we're not trying to avoid implementing thermal control plans. But you need to use thermal control plans to facilitate the work, reduce temperatures, control temperature, and minimize thermal cracking. Thank you.